Hello everyone, I welcome you all to the detailed lecture series on molecular dynamics simulation. Most of the students, researchers and scientists are inclined only towards the hands-on performance of the simulation, but they fail to perform it in a right way, and the data that is generated from such simulation is irrelevant to the research topic. The reason for the failure is the lack of understanding of the theory behind MD simulation. In this course, we will try to gain the complete understanding of the important theoretical concepts of the MD simulation and apply these concepts while we actually perform the simulation using software such as GROMACS, NAMD, and LAMMPS. It will help you in better designing of your simulation system, generate the relevant data, elucidate different properties, and gain valuable insights in your own system. In addition to the theory, we will be performing practical tutorials where we will decide which properties of the system we want to study. Accordingly, we will design and simulate our system and try to predict those properties. We will learn to run the MD simulation using GROMACS, NAMD plus VMD, and LAMPS, and we will be doing their sample tutorials with complete explanation of the code. Most people fear the errors that arise while performing these simulations, and you do not have to worry about such errors as I will provide solutions to all the possible errors that you might encounter for each step of the simulation workflow. MD simulation has a wide range of application in the field of biotechnology, chemistry, material science, and pharmacology. Therefore, we will try to make this series as comprehensive as possible so that it can fit to all the viewers coming from different backgrounds. In short, you can view this course as a basic to advanced level course on MD simulation, and if you stay till the end of this series, you will be able to perform a really cool MD simulation on your own.
Let us discuss in brief about the course contents. Note that this is not a complete list of topics and more topics will be added in the respective course video in the future. So in the first lecture, which is the present lecture, that is the present video, will consist of the complete plan about this lecture series that I am discussing it right now. And this course will also contain, this video will also contain the MD simulation cycle, which is the most fundamental thing in the MD simulation. And we will be explaining it in the start at the beginning of the whole series. This repetitive five-step procedure, which is called as the MD simulation cycle, which will be the first topic of discussion in this lecture. In the second lecture, we'll be focused on different properties of the system that can be studied using MD simulation. What properties to study is highly dependent on the subject, that is whether you are studying biotechnology or chemistry or material science or pharmacy, and the research question under study. For instance, a biologist like me will study the properties like binding energy or thermodynamic properties of biomolecules like proteins, lipids, plasma membranes, as well as folding dynamics of some proteins. And on the other hand, in case of mechanical engineering students might be interested in knowing the mechanical properties like the stress, strain, then pressure, etc. about their materials. Chemists, on the other hand, might be interested in studying the binding properties of the drug molecules with their target proteins. We will study all such properties using MD simulation, and we will take inspiration from some benchmark research papers and try to understand their research problems and what properties the researchers aim to study of their biomolecules. In the third lecture, we will focus on in-depth understanding of the concept of force fields. We will learn about some common force fields like charm, then amber, then OPLS, Gromos, Martini, etc. that are commonly used in MD simulation using GROMACS or any other simulation packages. In the fourth lecture, we will understand the notion of differentiation and numerical integration, which are well-known concepts of mathematics. With the understanding of this topic, we will try to understand how values of velocity and displacement are derived from acceleration. With the understanding of the concept of differentiation, the process of force calculation from the interaction energy, which we'll be discussing in this particular video, will be more clear when you understand differentiation and numerical integration. But meanwhile, if you are not able to understand the differentiation and integration, I will add a link at the top of this video to other interesting and most insightful videos that would help you in understanding of numerical integration and differentiation in a more visual manner. In the fifth lecture, the topic of discussion will be the MD ensemble and the Monte Carlo simulation. Understanding the Monte Carlo simulation might not get completed in a single video, and this topic might continue over multiple videos, but we will try to make it as comprehensive as possible so that you can understand it more in a more better way. In the sixth lecture, we will be discussing the concept and the need for energy minimization and learn the different methods of minimization that are widely used. In the seventh lecture, we will be discussing the PBC, which is the periodic boundary condition, as well as the group concept, and enter into more algorithmic aspects of the MD simulation, including the notion and need for temperature and pressure equilibration, that is NVT and NPT. In the eighth lecture, we'll be focusing on the practical aspects of performing MD simulation, where I will start by explaining about different file formats present in GROMACS and move on to explain the general outline of all files, where I will also explain about each and every field that is present in each file and what information that field contains. With the understanding of all file formats in GROMACS, in the lecture 9, we will have a discussion on topologies involved in GROMACS. From the 10th lecture onwards, we'll be performing all the example tutorials provided on the GROMACS web page, along with the explanation of each and every command used in that sample tutorials, as well as the general syntax of the commands used in that sample tutorial. We will then move on to discussion of errors, that is all the possible errors that the users can encounter will be solved at the end of each demonstration. Errors encountered by users while performing the MD simulation that might be posted in the comment section will be considered, and solution for all of them will be provided in a separate video. We will then move on to performing some sample MD simulations using NAMD and BMD, and we will also follow the sample tutorials and discuss the errors encountered by the users at the end of each sample tutorial. Moreover, if the users get their own errors while following this tutorial, they can also post it in the comment section, and I will be giving answers to all of those errors in the comment section, as well as in a separate video where all the errors will be combined and a solution will be provided for them in that particular video itself. Similar sample simulation would be run using LAMMPS, and the possible errors will be explained and solved at the end of each demonstration in case of LAMMPS as well. Finally, we will wrap up this highly exhaustive series with two case studies where we will be performing some special types of simulation. So this is the complete plan of this course. This is going to be a really insightful series, and I want your participation to help me complete this course. So without further ado, let's begin with the MD sim cycle, which is MD simulation cycle, which is the first and most fundamental concept in the MD simulation.
Look at this animation and what do you see? This animation is the movie of MD simulation of a protein interacting with a drug molecule. On the surface, you could Just to see the movement of protein, the drug molecule, the ions, which are sodium or chloride ions, and water molecules that are present within the same system. This movement of various molecules come from the movement of individual atoms present within the molecule. Therefore, MD simulation is nothing but the movements of atoms in space. For performing simulation, one need to move or add motion to the atoms, and these movements should be realistic in nature. How can we add motion to these atoms? You might ask. To add a motion to atoms, we first need to establish the atoms in space. That means we need to assign initial position to the atoms. Any object in space has a location, and this location is defined by the x, y, and z coordinates of the atoms. As atom is also an object in space, its position can be defined by knowing its three coordinates. How we can get the coordinates of the atoms? In case of proteins, the structure is stored in the form of the PDB file, and such files have coordinates of each and every atom that is present within the protein. So the PDB files will be the source of the x, y, and z coordinates for each atom that is present within it, and therefore these coordinates will help us decide the position of each atom in space. In reality, atoms are never static. They are in continuous state of motion. Therefore, atoms should have initial velocities, and if the initial velocity of the atom is not defined, then we need to assign a particular velocity to the atoms in our simulation system. Defining initial position and initial velocity is the first and foremost step of the MD simulation. This information will be used in future steps to predict the new position and new velocity of atoms after a finite amount of time. So at the end of each simulation cycle, you will get new position of atoms and their new velocities. This would result in complete change in position of the entire biomolecule. And imagine if you repeat the simulation cycle over a number of times, your biomolecule will change the position numerous times. And if you record these new positions of the entire biomolecule frame by frame and run all the frames really fast, then you could see smooth movement of your biomolecule over a finite amount of time. Although you could move the entire biomolecule by adding motion to each of its atoms, these movements of your biomolecule should be realistic in nature. That means they should be energetically possible and favorable. Therefore, to accurately predict such new positions and velocity of individual atom from its initial values, we need to perform calculation with respect to time or by making measurement in a particular time interval. And this interval of time should be very, very small. By the term very, very small, I mean it should be the order of 1 femtosecond or 10 raised to minus 15th of a second. This is because atoms vibrate and move very, very fast. They perform approximately 10 raised to 14 vibrations per second. Therefore, to model this behavior of atom, we need to consider this finite amount of time to be very less. What happens if we do not consider this time to be that less? We decide to record the movement of an atom after 1 second. Then, from a perspective of an atom, in that particular 1 second, the atom has already vibrated many, many times and has changed its position thousands of times because the speed of the atom is 10 raised to 14 vibrations per second. And it would be quite impossible to predict the final position of atom after 1 second. Now we assume that one vibration of an atom takes about 1 femtosecond of time. that is 10 raised to minus 15 seconds, to make a single vibration or movement. And we know that the initial position of atom as well as initial velocity of atom, then after 1 femtosecond we can predict the final position of atom using Newton's law of motion. Therefore, we need the time interval to be very less in order to predict the final position and velocity of an atom from its initial position and velocity. To summarize all this information in one line, we could say that for getting started with MD simulation, we first need to know the initial position and initial velocities of all the atoms that are present within a system. And using this information, we will predict the final position and velocity of all these atoms, but over a finite amount of time. And this time interval should be of the order of 1 femtosecond. Now we will move on to step number 2 of our MD simulation cycle. Now we have initial position and velocity of each atom. That means each atom is in a state of motion for a finite amount of time. Now imagine in this time interval, atoms will also come in close contact to each other. They will interact with each other, and the distance between these interacting atoms uh, will be a finite amount of distance, and we will consider this distance to be the letter r. Moreover, moreover, the atoms would contain charges on them. So when two charged species, such as two charged atoms, are separated by some finite distance, that is r in our case, then there exists a finite amount of energy between them. And this energy is given by a famous equation called as the Coulomb's equation. If two atoms are oppositely charged and are present at a finite distance r from each other, then there is some finite amount of energy that can be calculated by the Coulomb's equation. And the nature of this energy would be attractive when two atoms are of opposite charges. And this energy can be repulsive when two atoms contain the same charge. Such energy that exists between atoms is called as the interaction energy or interatomic energy. If you describe the distance between these atoms such that new distance is r2, which is quite less than r, then this interaction or interatomic energy would be greater as compared to the former case. If the interacting atoms are of opposite charge, then attraction energy will be quite large enough that the atoms might be bonded together. If you continue to decrease the distance between the atoms, the interacting atoms will start to experience repulsion from each other. The interaction energy between two atoms increase rapidly due to the cumulative repulsion from the electrons and the protons that are present inside the nucleus of the interacting atoms. At this stage, the repulsion energy is predominant, whereas in the former two cases, the attraction energy was the dominant form of interacting energy between the two atoms. We would plot this relationship between the energy and interatomic distance to get a peculiar graph which defines this observation in a correct manner. This graph can also be depicted using a mathematical equation that defines the attractive as well as the repulsive energies with respect to the distance between the interacting atoms. This equation is called as the Lennard-Jones equation that gives the idea about the energy between the atoms when one varies the distance between them. Let us look at this graph in a bit of a detail. At greater distances, the atoms cannot experience any type of interaction energy, and thus the value of the energy is zero, which is depicted by a slope of the graph, which is almost zero. As the atoms come close to each other, there exists the interaction energy whose value becomes more and more negative as the atoms move close to each other. Negative value of the interaction energy indicates the presence of the attractive energy between the atoms. As the atoms close the distance more, then at a particular distance, let's say r, the interaction energy is the most negative. This depicts the strong attraction and stable bond formation between the atoms. If atoms come more close to each other, the interaction energy continue to rise and becomes more and more positive. This positive interaction energy depicts the presence of the repulsion between the atoms. So from the graph, it is clear that at very greater distances, there is no interaction energy between the atoms. Then as we reduce the distance between the two atoms, the attractive energy dominates as the interaction energy. And at a very small distances, electronic and protonic repulsion dominates the interaction between the atoms. Thus, from the initial position and velocity of atom, we can get the distance between the atoms and deduce the interaction energy between them. This computation of interaction energy between the atoms is the second step of MD simulation. As we know the interaction energy between the atoms, we can find the force exerted by each atom on another atom with which it is interacting. As you know, at a very less distances, repulsion occurs between two atoms, and both the atoms will try to achieve the stability. That is, they will lower this interaction energy to achieve its lowest value and to obtain a stable state. This can be achieved by increasing the distance among them, that is, between the atoms. This is achieved by the application of force, and this force will be opposite to that of the movement of atoms towards each other. The force is nothing but the repulsive force that pushes the atoms at a finite distance r. How can we calculate these repulsive or attractive forces that enable the atom to achieve the lowest interaction energy between the atoms? This can be achieved by calculating the slope of the graph. Slope of the graph can be calculated by differentiation of the interaction energy with respect to the distance r. With small change in interaction energy with respect to the distance, there is also a change in the interacting forces between the atoms. To summarize the third step uh, in one line, force acting on an atom can be calculated only if you know the interaction energy that exists between the atoms of the system. Just differentiate that interaction energy with respect to the distance r, and the value obtained will be the force acting on the object or on the atom, will be the force acting on each atom exerted by their partner atoms with which they are interacting. So what is the force? According to Newton's law of motion, especially Newton's second law of motion, the force acting on an object is equal to the product of its mass and the acceleration. From the third step, we obtain the value of force, and Newton's second law of motion, we will obtain the value of acceleration. From this acceleration, we will obtain the value of velocity and new position of atom in space. Thus, finding the acceleration from the force is the fourth step of MD simulation. We have the value of acceleration, and we need to find the value of velocity and displacement. Therefore, we need to perform a reverse operation to that of differentiation of the velocity. Therefore, we need to integrate the acceleration term in order to obtain the value of velocity. Do not worry if you fail to understand the notion of integration and differentiation. We will be discussing these concepts in the future videos. Meanwhile, I will suggest you a particular video at the top that will make you visualize the concept of these two terms, that is numerical integration and differentiation. Similarly, we know that change in displacement with respect to time is called as the velocity, and this can also be represented by the following equation. Velocity is the differentiation of displacement with respect to time. We need to perform the opposite of differentiation, that is integration of this particular equation to get the value of displacement. Now, displacement is a vector quantity. In simple terms, it means you can know how much an atom has moved from its initial position and in which direction it has actually moved. Once you know the value of velocity and displacement, you could easily know the final position of the atom as well as the final or the resultant velocity with which the atom is now moving. Therefore, deriving the new values of velocity and displacement or position of all the atoms is the fifth and final step of the MD simulation. As mentioned earlier, all the five steps are performed for a single time interval, and this time interval, as mentioned before, is of 1 femtosecond. So whenever we perform MD simulation, we are repeating these five steps with a time interval of 1 femtosecond. So whenever you are told to perform MD simulation of say 1 nanosecond, and 1 nanosecond is equal to 10 raised to 6 of femtosecond, so you would be performing 10 raised to 6 cycles of this MD simulation, that is 10 raised to 6 times these 5 steps in order to simulate a molecule for over 1 nanosecond. In summary, once we have the initial velocity and initial position of all atoms, then we move on to calculating the interaction energy that exists between different interacting atoms in the system. Knowing this energy, we would differentiate it with respect to the distance between the interacting atoms. We will calculate the resultant force acting on a particular atom, and we will calculate this total force, and using Newton's second law of motion, we will obtain a value of acceleration. We will integrate, that is, we will perform numerical integration of this acceleration to know the final velocity and final position of all the atoms that are present within the system, or predicting the final values of velocity and position from the initial velocity and position of all the atoms over a finite period of time of 1 femtosecond is called as the MD simulation cycle. I hope you have understood this concept, and in the next video, we will move on to explain the different properties that can be studied to that of the biomolecules using MD simulation.